Computing relies on microscopic electrical pulses, rigid, binary, and entirely mechanical. But human logic is fluid and abstract. Every line of code written is an attempt to map that organic intent into the specific, fixed instructions a processor can actually execute. Mapping every single action directly into ones and zeros is too complex for large-scale software. Instead, we use structured methodologies to manage the code, allowing us to build complex systems without communicating in raw binary. This is the abstraction ladder, a visual map of programming paradigms. These are distinct approaches to problem solving that exist on a gradient of abstraction, separating the programmer from the underlying hardware. We climb this ladder to understand how we control modern computers. We start at the hardware memory layer with assembly, move through the control flows of the imperative paradigm, and finish with the high-level logic of declarative programming. These paradigms are not just syntax choices. They are structural decisions that dictate exactly how much manual control the programmer retains and how much they delegate to the machine. At the lowest level of programmable abstraction is assembly language. It belongs to a family of low-level languages that uses mnemonics to interact directly with the CPU's special-purpose registers. In the little man computer architecture, a CPU accumulator connects to RAM. Instructions have two parts. The opcode dictates the action, while the operand holds the memory address. To find a modulus, the pointer loops through memory, repeatedly subtracting values until positive. Early memory constraints limited the physical size of the operand. This meant there was a hard limit on how many individual memory locations a programmer could access. The architectural solution to this was the development of addressing modes. These modes are part of the opcode and specify exactly how the system should interpret the operand. In immediate addressing, the operand is the actual binary value the instruction must use. Direct addressing, used in the LMC, treats the operand as the specific memory address where the data is stored. Indirect addressing provides the address of a register which holds another address. This is where the data is actually located. Indexed addressing adds an offset from an index register to the operand. This allows programmers to iterate through data stored contiguously in memory, like arrays. Assembly provides total hardware control, but mapping every instruction one-to-one is too slow for massive applications. Scaling upward requires the next step on the ladder. The imperative paradigm shifts the focus toward code that specifies the exact step-by-step actions the machine must perform to reach a goal. Procedural programming is a widely used imperative style. It groups instructions into procedures and uses built-in data structures like strings and arrays. In structured programming, control flow uses four main structures. Sequence executes linearly, top to bottom. Selection uses if statements to branch the code based on conditions. Iteration uses loops to execute code multiple times. Recursion repeats a function calling itself until a base case is triggered. While procedural programming handles algorithms efficiently, managing data states across massive, interconnected systems can make the code structurally unstable. Object-oriented programming, or OOP, was designed to manage this complexity by focusing on reusable components and scalability. The core of OOP is the class, a template defining an entity's attributes and methods. Through instantiation, this template creates unique objects. To ensure reliability, encapsulation keeps attributes private. Access is only granted through specific getters and setters, protecting internal data from unauthorized manipulation. Another key property is inheritance. A subclass, like biography, inherits the methods and attributes of its superclass, book. It retains properties like author and title, but adds its own unique subject, allowing programmers to reuse code while making specific changes. Polymorphism further extends this by allowing objects to behave differently depending on their class context. This can happen through overriding, where a method is redefined within a subclass to produce a different output. It also includes overloading, where passing different parameters into the same method yields different results. OOP requires significant advanced planning and is often inefficient for small problems. However, its modular structure and data protection make it the standard for complex software engineering. In the declarative paradigm, we move away from step-by-step instructions. Instead, the programmer simply states what the final result should be. The details of how the result is obtained are abstracted from the user. The programming language engine determines the best path to find the answer. The functional paradigm uses a core of reusable mathematical functions. These programs consist of combined function calls, making them ideal for high-level mathematical processing. The logic paradigm defines a set of facts and rules based on a problem. Users then use queries to find specific answers within that set of rules. Because they remove the burden of manual control flow, declarative languages are common in expert systems and artificial intelligence. This matrix organizes programming languages based on their degree of abstraction and their control flow. Choosing the right one depends on matching the problem to the paradigm. Procedural languages are efficient for simple algorithms and direct data manipulation, sitting midway up the abstraction axis. Object-oriented languages plot higher on the axis, providing the protection and modularity needed for scalable software. Declarative languages occupy the opposite quadrant, suited for AI and rule-based systems, where the logic of the result is more important than the steps taken. Despite these high levels of abstraction, software cannot escape the physical reality of the machine. Every command eventually collapses back down the ladder. Whether you are running a logical query or a polymorphic method, it resolves into a basic opcode and operand mapped to physical silicon memory.